Good morning. Welcome to our grand rounds this month. One of our kind of, in a sense, we have a distinguished lecturer who's with us today, even though we haven't officially started our distinguished visiting lecturer grand rounds, which will be starting up in 2017. I was very excited and very eager to get David Redish out here to, in a sense, get us going in this direction. And this is a direction in which we seek to bring out people who have an international reputation and an aspect of psychiatric research and or psychiatric neuroscience research, really here to start stimulating us in the department about the new research and indeed clinical directions that we can and should be moving in, and also to exemplify ways in which we can have collaborative relationships with such researchers in a way that is only being done in a small handful of places around the country and around the world. So it's very exciting for me to have David here as kind of kicking off this new approach to our grand rounds. So I was very excited to learn this morning as I was reviewing David's CV that he is not only a world-class neuroscientist, but he is also a published poet and playwright. And in fact, I learned just a few minutes ago that a play just went up in LA. And so I hope you'll just tell us a little bit about it. But I thought, I could do the usual academic introduction in which I go through his CV and his many honors and awards. I'll point out just a couple of things, but then I'm going to read a poem that he wrote and show you a book. But in terms of his educational background, David got his bachelor's at Johns Hopkins with a double major in computer science and in writing seminars, his master's at Carnegie Mellon in computer science, his PhD in Carnegie Mellon in computer science, and did postdoc work at the University of Arizona. He has been faculty since 2000 and is also a distinguished McKnight University professor and one of a small handful of such professors. And my understanding is that also that there haven't been many such of the professorships handed out in recent years, and he is one of the few who has been able to receive that honor. His work, perhaps the simplest way for a psychiatric audience to summarize his work is to show you and tell you the title of a recent book, which is The Mind with the Brain, How We Make Decisions and How Those Decisions Go Wrong, right? So what could be more to those of us who do clinical work and who think about the lives of our patients and how we can help them. David is a computational neuroscientist, which means that he thinks about how does the brain represent the information that is coming into it from the environment? How does it compare that information with information that is previously stored? And how does that information then get used to sort of guide the next stages of information processing in terms of our action outputs? So with that introduction, and before I turn the podium over to David, let's just read a poem from Chapter 2, The Tale of the Thermostat, which I don't know what that refers to, having not yet read the book. Here's the prologue to that chapter. Jet exhaust shimmers above the tarmac. I remember the strength of swans on the lake up north, their wings stretching forward, beating back. Acceleration pushes us into our seats and we lift into the sky. Thank you for that moment of beauty. And now for a different kind of beauty, scientific beauty.
Thank you. So it's great to be here, and I'm actually not going to spend the day reading poetry, nor am I going to talk about the play. Although I'd love to talk afterwards, because it turns out it's actually very surprisingly psychiatric about things that when I wrote it I didn't know and do now. What I want to talk to you about today is this new field, this new zeitgeist that's kind of coming around called computational psychiatry. Let's turn this on. Called computational psychiatry. And I want to start today with a caveat. Okay, I'm Dave Redish, that's a caveat. Those who know me will know that is a caveat. I'm a PhD, not an MD, right? The old joke about phony doctor, right? I'm a PhD, not an MD. Moreover, my PhD's in computer science, okay? My thesis was bringing together models of hippocampal function, asking how can you bring together and resolve the experiments that were in showing about animals in space and animals and memory, and how are those the same thing? And I was able to reconcile that debate in my thesis work, and that led to the first book, which I do not expect any of you to read, which basically was, as I said, the thesis work. I had not done any experiments at this point, and as a postdoc, I learned to do experimental neuroscience, where basically we ran rats on mazes and asked, how could we manipulate the space around them and change their behavior? And then I came to Minnesota, where in my lab we study these cute little brown fuzzy creatures called rats. So why am I talking to you today? Why am I here at a grand rounds in a psychiatry department? And the reason is because in 2003, I noticed something, and I wrote a paper. And I like to think of it as a kind of a look over here paper. Because what it was a recognition that you could think of addiction as a breakdown in the computational process that was going on, that the learning and memory people had known for years. And many of those papers would end with a sentence saying, the importance of this for addiction has not escaped our notice. But most of us, then I found, most of the addiction people, it had escaped their notice. So I wrote a paper, it got into Science, and suddenly I'm the addiction theory guy. But this also, it's not the only paper at this time period, but there were a couple of other papers like this that kind of started off this idea that we could think about addiction and other psychiatric disorders from a computational perspective. And this has now exploded, including, stuff, as I like to say, from Zurich to Australia. There's a new transcontinental computational psychiatry working group that has found the one time in the country every month where you can actually log in from both New Zealand and Zurich. That's a pretty far split. But there is the book that Sophie was mentioning. There's a new book, which I'm going to talk a lot about today, done with this guy, Josh Gordon. A couple of other books that I know are in the works. And at least, I would say, 3 to 5 other books which have some aspect of computational psychiatry in their title. And there's now a new journal coming from MIT Press. So something's in the zeitgeist, something's happening. And what I want to do today is I want to talk to you about that. And the key here is to think about it in terms of information processing. That is, your brain is fundamentally an information processing device. Whether you are hitting a triple axel jump, or a student learning from a lecture, or actually even a clinical practitioner trying to figure out what's the right treatment for your patient. It's all about information processing. Now, that doesn't mean your brain's a computer. That's a different statement. But what it does mean is that if we talk about how does genetics, how does pharmacology, how does changes in the environment affect behavior, they all affect behavior through the translation of the brain. And so fundamentally we have to ask, what is going on within the neural circuits, within the brain, within the computation that this brain is doing? And that means that if we have an underlying dysfunction, that underlying dysfunction is going to be translated through this computational dysfunction into an observed dysfunction. I'm going to explain what all this is. That's my goal today, to explain what I mean by this. So, why am I, again, coming to talk to you? In part because of this wonderful conference that I helped organize called the Strungman Forum. So Strungman Forum is an ongoing conference, and the idea is you take experts in some field and you lock them in a room together and make them write book chapters together. And I mean that literally. It's in the suburbs of Frankfurt. There's nowhere to go. So a couple of us in the computational world had been talking about this idea of, well, it'd be great to actually, have a Strungman Forum on this computational psychiatry thing that's coming up. But none of us knew the clinical crowd. I had a good friend, Josh Gordon. Josh I know through our rat work. Josh does mouse recordings in the same kind of spatial tasks, decision tasks that I do. And so I know him from that world. And then I was talking to him, I said, wait a second, don't you have a clinical side? Do you know the clinical people? And so Josh and I wrote up a proposal. It got accepted as a Strungman Forum. And basically, I brought 22 computational people, and Josh brought 22 clinicians. And as I said, we locked them in a room together, and we wrote a book. Now, some of you may be saying, wait, I know that name. Why do I know the name Josh Gordon? The reason is because this is the Josh I know, and this is the new Josh. So Josh just took over to be director of NIMH several months ago. And so this book is, in fact, a large part of what I think he's going to talk about there. And I say that because he had an interview at Science where he mentioned a few things that I thought was particularly interesting, right? He says, what are your priorities? He talks about neural circuits, computational psychiatry, bringing more computational formalism to psychiatric research at all levels, basic clinical and perhaps even implementation research will help us do our job better. And at the end of this interview, he has a fascinating sentence that I'm sure most people didn't understand. It may be mathematically that combining these two things, the RDoC assessment and the DSM assessment, gives you more information. This is, in some sense, almost a code, because the consequence of this meeting, the 44 of us, those 22 clinicians and 22 computational people, what we ended up at the end of that meeting was that mathematical method of combining these two. And that's where I'm going to end. My goal today is to take you to understand this last sentence. Okay? So the talk today is going to be in 5 parts. I'm going to talk first about what I mean by computational perspective, because I want to make sure that we're all on the same page with that. Then I'm going to talk about a key concept, this concept of a failure mode that I think is kind of the way to take computation from computation into psychiatry. I'm then going to spend the middle part talking about kind of the work that I do, because part of this is also for me to come and say, look, this is what I've got. You know, I'd love to collaborate, I'd love to connect up, I'd love to see if we can make progress just from me, but also in addition to this kind of overall stuff. And then I'm going to take this to the problem of the clinic and really talk about stuff, honestly stuff I learned about at this Strungman Forum, and then end by trying to provide an explanation. I'm going to do that by connecting back up to the pieces that we've talked about. So first of all, what do I mean by the computational perspective? Most people, when they hear computational neuroscience, computational modeling, computational psychiatry, what they assume we're talking about is complex models of neural things. Whether it be a circuit diagram of axons where you kind of model each axon by some complex equation, or Eric DeSchuetter's famous 3,000 compartment Purkinje cell, or the box and arrow kind of computational information processing pathways that I did for my thesis. This is not what I mean. What I mean instead is the statement about information processing. The statement that when we talk about these things, we're talking about computational processes. And that we have lots of models of how these processes work. And it's that concept of looking at it from a computational perspective that I want you to be doing. And let me give you my favorite, call it the TED level algorithm, a TED level example of this, because I think this really gets at what I'm talking about. Representation, one of the main discoveries of computer science over the last 50 years is that how you represent the data matters. So imagine that you have sorted your bookshelf. This is not my complete bookshelf, but an example that I made. And I've sorted it simply by author, just as many people sort their books. And this is great if my daughter wants to find her next Land of Stories book, right? She knows the author, she can look for the author, she can say, aha, the next one is now the next one in the series. However, this is not a particularly useful organization if her goal is to find a book that's large enough to lift the computer monitor up so she can see it really well to play her computer game on. If she wants that, actually sorting it by size is a much better idea. Right? It's not that sorting by size is worse or better. It's that how you've represented the data makes it easier or harder for different algorithms to find the next piece. And in fact, what algorithms will find depend on these data representations. And that's a computational statement. And that's what we're going to use. Okay, so now let's go to the concept of this failure mode. The idea of failure mode comes from reliability engineering. And the idea is it's a vulnerability inherent in the machinery, in the structure of the system. This is the 35W bridge collapse, which is actually about almost 10 years ago now. Some of you may remember this. And what happened, of course, is that it broke at two very specific points. Notice it didn't break randomly. It broke at two very specific points and collapsed into the river. And it collapsed in because the gusset plates were built not to spec. They were they were not as strong as they should be, and they had bent. They had rusted and bent. They were no longer straight. And what that meant was that the bridge was weaker at the points where these gusset plates were holding it up, which happens to be right here and right here. Right? There's a vulnerability inherent in how this system was built. And so you have this idea of what the reliability engineers would call a physical failure mode. You have some combination of rusting and age that makes the bridge of lower strength. You have some extra weight, whether it be sand trucks or traffic. Luckily, this time it was sand trucks. There was actually very little traffic on this. And this created excess weight. The combination creates a bridge failure. There are also computational failure modes. My favorite example of this is a computer virus. Your computer program on actually these days, your cell phone, your tablet, or your laptop, but any computer, has a normal code path of processing that it's trying to do. But within that, there are hooks, there are ways of getting into it that a virus, such as the blaster virus, this is not enough to do anything with, so that's not going to help you. This is off Wikipedia. The virus will come in and create an unintended code path to create viral things, to do viral things rather than normal things. And actually, for the record, this is what real viruses do, right? They come in to a cell, they change the genetics, right, which creates an unintended code path. So virus is actually the right term for this stuff. So let's take a look at a neurophysiological failure mode and what we mean by this, okay? So I like to think of this in terms of levels, right? So if we look at epilepsy, for example, there's a whole slew of channel dynamics that can change, that can underlie epilepsy. These are the genetics that we were talking about. Those genetics create a change in the excitatory inhibitory balance within the neural circuits. That's the computational level. That's the brain level. These genetic changes, many genetic changes, get translated into this excitatory inhibitory balance that then creates a behavioral outcome that we can observe. Right? And this is an example of a failure mode and looking at that failure mode through the system. So another example of a failure mode, you can think of actually from a psychiatric perspective of OCD. So classic things of OCD, right? You think that person has to lock the door 3 times or something like that. What is actually driving this? Well, there's several hypotheses, and the computational perspective says, I don't know which this is, but these are the hypotheses we're going to work from. Right? One is that there's an imbalance between different modes, one of which says, I'm going to do this, and what's the outcome going to be? We'll talk about deliberation and habit later. But another is just, that worked, do it again. And if you have something that says, that worked, do it again enough times, you may end up in a cycle. But you could also end up in a cycle based on an inability to recognize completion of the target. What if I actually don't represent that I locked the door? Right? I locked it, but did I lock it? I don't know. I'm not sure. Did I lock it? I better go back and check. Or it could actually be an overintensity of the anxiety predictions of this outcome, right? I'm 90% sure I locked it. Maybe for you that's okay, but 10% chance of somebody breaking into my house is going to freak me out. So I need to go and make sure, not 90%, I got to make it 95% or 99%. And one of the things you'll find is people who are doing these two will actually create what we would call episodic triggers. They'll actually do things to make it easier to remember. When I used to leave the house, my daughter and I, when she was young, we would always say, bye-bye garage door. And then later I could ask, did I say bye to the garage door or not? Right? Marking it episodically makes it easier to remember that you have, in fact, locked the door. Right? But each of these, and this is kind of the main point I'm going to try to communicate, these are different underlying dysfunctions. They're probably going to need different treatments. And these are examples of computational failure modes. These are failure modes. Now, what caused this? It could be a learning thing. It could be an imbalance in the neural circuit. It could be genetics. It could be lots of things, right? But under the end, you have a computational failure mode driving this. So this also, as I said, has implications for treatment. If we understand these failure modes, we can do things like provide proper inspection to make sure that what is the actual weight, what is the actual strength that this system can take. And we could do things like strengthen the bridge or limit the weight. We can provide treatments aimed specifically at these failure modes marked once we know what they are. Okay. So now, in part 3, I want to take you through some of the work we do, and I'm going to give kind of a relatively superficial layer on it because I don't want to go too much in depth. I could spend semesters talking about this, so I'm not going to. I'm just going to give you kind of a flavor of it. But what we work on, as Sophie mentioned, is how you make decisions and how those decisions go wrong. And so the first thing we have to do is actually operationalize what we mean by the word decision. And one of the problems is we end up in arguments over that. So I'm going to cut all those arguments. I'm going to say if you take an action, you've made a decision. Simply put, I'm just going to define decision making as action selection. And that works if you're a rat deciding where food is buried, a monkey deciding where to look its eyes, a rat running on a maze like they do in my lab. And yes, these are Lego bricks. We build all our rat mazes out of Lego bricks. They are perfect rat maze construction materials. It also works if you're a graduate student, I suppose, or a resident. I think of this from a computer science graduate student perspective, titrating just how much sugar you need to keep you awake, but not too jittery to actually do the programming you have to do overnight. It works if you're going gambling or not, if you're taking drugs. Obviously, any drug that you're actually taking, you're taking the action to take the drug. It also works for big decisions. When you talk about things like going to college, in the end, where you go to college, you're pushing a button, you're signing a form, you're taking an action. And big decisions like getting married, this of course is from The Incredibles, and the secret is you have to be flexible. So, okay, given that it's about actions, this means, again, what's the information that underlies it, right? Decision-making is a combination of past experience, sensory cues, and goals, and they kind of combine in this wonderful mixer, and they produce action. The key here is, as I mentioned, how you represent the data and how you store it, how you recall it, how you access it, changes how this decision process works. And it turns out that at least in mammals, there seem to be at least 4 different decision-making processes that interact, each of which uses a different algorithm. The simplest one is reflexes. And you can say, is a reflex really a decision? But it is. If the stove is cold, you're not going to move your hand. If the stove is hot, you pull your hand back. You are, in fact, taking an action or not based on information in the world. Now, the goals and the stimulus-action pairs, those are hardwired into your circuit. And they're hardwired through an evolutionary learning. And computer scientists have known for many, many years that genetic algorithms that learn by this kind of random search process, are very, very good at long-term kind of solutions. So we are seeing this is, in fact, an evolutionary learning. The storage is done hardwired into the circuit. It's not very flexible within the lifespan. And things like homeostasis are reflexes. The changes in your body in response to things. This is what the nicotine patch is for. It's to pull your homeostasis back down slowly while other systems can actually deal with it. A second system is called Pavlovian action selection. I'm going to apologize right now for the term. It's not a term I invented, but it is what Pavlov's dogs were doing. I love this picture. This is from Nobel.org, because Pavlov was actually the first winner of the Nobel Prize in Medicine. And the key here is that what you're actually doing is it is an action. You're releasing a pre-wired action under the right condition. So the dog basically releases this salivation in response to the bell after making this association. And the key is that these are actions that you've got to get right the first time, like running from the lion. Think about running from the lion. You don't get a chance to learn to run from the lion. You got to get that right the first time. But what you can learn is that when a lion is stalking you, there's a rustle in the grass. And that rustle in the grass produces fear and makes you run. The key is that this system can learn to run from the rustle in the grass. What it cannot do is learn to do jumping jacks in response to that rustle in the grass. And from an addiction perspective, things like attention and approach are key components of this Pavlovian system. This is from one of my favorite shows, The West Wing, where John Spencer plays Leo McGarry, who's a recovered alcoholic, and his political enemies are having a meeting with him, and they are drinking 100-year-old scotch, and he cannot take his eyes off that scotch. Right? But also, it turns out that a lot of social dynamics in humans are Pavlovian and use this system. And one of my favorite examples is laughter. If a person is missing their motor cortex, they cannot smile on command. They cannot voluntarily. I'm not too keen on using that word, but they cannot smile when you say, I'd like you to show me a smile. But if you tell them a joke, you get them, their friends hanging out and laughing, they laugh perfectly normally. And the reason is because that laughter is from this Pavlovian system. The third system is a search and evaluate process, a process that actually imagines a future, creates a simulated future, and then runs that through evaluation processes. So if I'm trying to decide where to take my family for vacation, and I say, well, should we go to Stonehenge? Should we go skiing? It's what would life be like if I went to Stonehenge? What would life be like if I went skiing? The key is, it's not some quantum mix of the two. It's a serial creation of one and then the other. And my lab's done a lot of work on this one in particular because it turns out that rats deliberate over choices. And this is very much what got us shifted in my lab from the spatial stuff into the decision stuff. Because what it turns out is that sometimes a rat will come up to a choice point and it will stop and look back and forth. It's a process called vicarious trial and error, which is abbreviated as VTE. And we know now during this VTE process, what you see are sequences in the hippocampus of the rat running ahead of the animal to one goal and then to the other, around corners all the way to the goal, back and forth. And in fact, we have pharmacological manipulations we can do which can change how decisive the animal is. And a more decisive animal only searches in one direction and then makes that decision. Whereas an indecisive animal will in fact search back and forth and represent both options. The key is it's not just that the hippocampus is sweeping ahead of the animal. What you actually also see is evaluation structures. The ventral striatum or nucleus accumbens and the orbitofrontal cortex represent the goal the animal's going to get and evaluate how good that goal is. And we can do this because we have technology whereby we can actually record from large ensembles of neurons and we can decode the representation within that ensemble. And that's very much kind of the world my lab lives in most of the time. One of the consequences of this is that the computational system that does deliberation is actually to create a simulated world and pass it down to the same evaluation structures that you use to evaluate the current world, which is actually how I'd build it if I were building a circuit. But it is how evolutionarily the system has ended up getting built. And what that means is the same system that says, I'm hungry, is the same system that says, put food in me. And I love this example, is that this is why when you go to the grocery store on Sunday, if you're hungry, you buy more food for the Wednesday, right? Because you imagine yourself, say, okay, the me on Wednesday, how much food do I want? Right? Well, you create a simulated world, pass it to your current system. Your current system is hungry, it wants more food. This is crazy. How hungry you are on Sunday is very unlikely to predict how hungry you are on Wednesday, at least for most of us. Okay, yes, this is Homer Simpson. Homer would buy donuts. The fourth system is this procedural habit system, because if we're deliberating over choices, it takes just much too long if we have to respond quickly. So for example, if we are, hitting a ball and, that's coming at us, we don't have time to say, well, if I put my hand here, it'll bounce over there, but if I put my hand here, it'll bounce over there. What should I do? I don't know, I should create a simulated world and, you're lost. It's gone, right? There's not enough time. And it turns out that what this fourth system is actually doing is recognizing a situation, which is a whole perceptual stuff that I'll talk in a minute about, And then, with that recognition, passing it to an arbitrary action chain that is well learned. And we know this happens in cortex. We know this happens in the dorsolateral striatum, also known as the caudate nucleus. And what's happening is somebody like a Ted Williams has practiced swinging a baseball bat so many times that he has learned to recognize the difference in the spin of a fastball versus a curve. Right? I can recognize that spin when it's slowed down like this, but if the ball's coming at me at 100 miles an hour, I'm pretty sure I would not recognize that difference. Because I have not trained my perceptual system up to do that. Right? This is not something that he was born with. This is something that he practiced and created this arbitrary action chain. And so the idea here is how we've represented past experience, sensory cues, and goals is different in each of these four systems. Right? And they are optimized for different situations. One of the things that is, in fact, wide open right now, it's a great question, is how do you decide which system drives? What if they say different things? We don't know this answer. This is actually what I like to think of as the ignorance question. This is a question that we didn't know was a question, but now that we know that there are these systems, how do you deal with this conflict is, in fact, a new question. And that's one we're working on, but we don't have an answer yet. If we were going to build a full box, a full kind of decision system, these four are the action selection, but there are other components like perception, and I mentioned situation recognition, motivation, what is motivation really, and what is action really. And I want to do one slide on each, and then I want to come back and start talking about kind of this bring it back to psychiatry. So, we don't see colors, we perceive objects. We don't hear sounds, we perceive music. Right? This is my favorite painting of Picasso's Pan, and I can see the motion and the emotion and emotion in this character. That's not a character. That's black lines on a piece of paper, right? But I see this satyr playing a flute. I can almost hear the flute. And many of you have probably seen this. Is this a B or a 13? It depends on what context you're in. Right? Everybody sees this as ABC, and everybody sees this as 12, 13, 14. But in fact, these are identical. Right? Perception is its complicated computational process. And a lot is known about that. We could spend days on it. Again, I'm just pointing out it's a computational process. A good question is things like motivation. What does it mean to be hungry? Obviously, in part, hunger is about being low on energy, your stomach needing food, your body needing food. But also, we can have cues, right, that make us hungry. And we can actually feel hungry and feel full at the same time, which is a fascinating statement. And suggests that motivation is a much more complicated computational process that we really need to open up. And even in terms of actions, right? When I say action selection, I'm not really talking about how you actually put one foot in front of the other. I'm talking about deciding to walk, deciding to actually walk back and forth. And we don't usually think about that. We think, I'm going to walk over there until our walk changes. One of the first times I saw this, a colleague had sent a physical therapist who had been having problems with her Iraq war patients in the early 2000s. And apparently they had leg damage, and that was causing memory problems. And she was pretty sure memory does not reside in the leg. They did not have head trauma. And she was trying to figure out what's going on. And at the time, I was doing a lot of memory stuff. My colleague sent this physical therapist over to me to try to tell me what was going on. And it turned out what was going on was that these patients would be on one side of the kitchen, decide they wanted, say, milk from the refrigerator, walk over to the refrigerator and forget what they wanted, which was incredibly frustrating. And I said, I know what's going on. What's going on is that they're using their deliberative system, which contains that active memory, to learn how to walk again. And the problem is that active memory has a limited capacity. And so one thing they could do is know that that's coming. They could write it down, and then when they got there, they'd have it. But honestly, if they just learn to walk, they just rebuild their central pattern generators and figure out how to walk with their new artificial leg, they'll be fine, and the memory problem will go away. And it turned out that was what she really wanted to hear. She wanted to hear this wasn't actually a memory problem. This was just a temporary thing, and she could reassure them, and things would go on. And I like that because that's a case where we understand a very surprising thing because of all of this basic neuroscience research we've been doing. So I want to point out that this whole concept of computational processes underlies the NIMH RDoC system. Many of you have heard of this. This is NIMH's attempt to create a taxonomy of underlying features to be looking at psychiatrically. So things like threat assessment and disappointment and affiliation and self-knowledge, sleep and wakefulness, things like that. Now, is this the correct taxonomy? That's an open question. But in fact, I'm going to point out it doesn't have to be the correct taxonomy. It has to be a taxonomy that can get us moving in the right direction. Because the Strungman Forum result is going to get us to the point where we can build on this. And that takes me to this last two parts where I'm going to talk about the problem of the clinic and actually translating this stuff and then this hypothesized way forward. So as I mentioned, this really comes about because of this Strungman Forum where we took 22 computational people, that is people like me, people who don't usually think clinically, and 22 practicing clinicians, people from everywhere all over the world who run actual clinical research labs, and many of them in clinical practice, some of them involved in writing things like the DSM and stuff like that. And we locked them in this conference and we made them write book chapters together. And the key is that you have these chapters that are built out of 11 people, right? And we very carefully divided this so it was half computational, half clinical. And they have to write a chapter they're willing to put their name on. And you have to imagine these are not people with small egos. Right? So getting a language that everybody would agree on was a fascinating process. We had about a week, about basically 1 full week, and it took us till about at least day 3 or 4 before we were even communicating language. Right? Just learning what some of these terms meant on each side. What's a normative process? What's a process model? What's a proband? Right? Just getting these languages took us 3 days. But we got there, and I think you'll see we got somewhere really interesting. So there are 3 major problems translating all this stuff I've been talking about into the clinic. One is this idea of equifinality and multifinality. Again, 2 words I had to learn. The second is this point about trajectory, which as computational people we tend to ignore because trajectory is hard. And this necessity of categorization, which I have to say was very surprising to me. So the idea of equifinality and multifinality is that multiple things have multiple sources, right? It's not that you just had lower strength that created the bridge failure. It's the combination of lower strength and excess weight. And there are multiple factors can combine to create different symptoms. So in one patient, you could have the same set of problems and create symptom A, and this different patient have that same set of problems and create symptom B. So you have both. It's a many-to-many mapping, and it's not trivial. The second issue is that many of these diseases tend to be trajectories, both within the disease itself and through life, right? The human lifespan is a trajectory. A physical dysfunction in childhood is going to create a different set of symptoms than that same physical dysfunction in adolescence or adulthood, right? And of course, these processes build on each other, right? I'm probably preaching to the choir here on this stuff. This is the stuff you guys were all telling us. And one of the things that I found fascinating, I think is really important to remember, is that there's a lot of pathways through the outside world in this, right? So if you have somebody with some sort of mental trauma, that could create sleeplessness or anxiety. But of course, sleeplessness creates an inability to cope with the situation, which creates anxiety, right? So you can actually have processes in the world that create second and third order mental dysfunctions that can create loops. And we need to start, when we build these models and talk about this stuff, we have to take this into account. And the third piece is categorization and the necessity of categorization, both for communication to patients and how apparently important it is for a patient to hear, you have disease X. You have this thing I can name. Naming something gives you power over it. A communication between physicians. How do I know that the group that you're using is the same as the group that I'm using? Well, we have a set of categories, and we can categorize it, and so we can compare them. And again, I'm sure, again, this is probably something you all know, but the importance of organizing this stuff for insurance purposes was surprisingly important. And of course, the DSM does a good job of categories. And one of the things that I was surprised to find out, because I've heard all these complaints about the DSM, is the DSM is actually quite reliable. Two different psychiatrists will produce the same outcome, they'll give the same labels to the same patients within the DSM. So the key here came with this very surprising breakthrough, and I still remember the day in our group where one person sat up and said, "Oh, the key is," and we all said, "Yes!" And then I watched 3 other groups literally make the same realization. The realization is that diagnoses are observations, not syndromes. And the DSM crowd had always assumed that they actually claimed to be atheoretical. Those of us in the computational world will tell you there is no such thing as atheoretical. It just means you don't know what your theory is, but there is a theory there, and it helps to actually state what it is. But the idea that the DSM categories reveal an underlying dysfunction has been the unspoken statement of the DSM from day one, and it still is. Hold on, we'll get there. It still is, and the key is that if we replace this not as stating that there's an underlying syndrome, but instead state that the DSM is an observation, and that this is an observation like saying you have a fever. I diagnose you as ADHD, I diagnose you as whatever, is equivalent to saying you have a fever. It limits the set of the underlying syndromes, that underlying dysfunctions you probably have, but it doesn't state which one it is. And when you do that, you end up with this very complicated, don't run away, I know this is math. I'm going to explain this, and we're not going to go through the math in depth. But we end up with a very clean answer. And the answer is that there are these signs and wonders, as I like to call it. You have signs of things, signals, things like symptoms, things like instrumental measures such as brain scans or the AXCPT test or a SCID. And you have diagnostic categorizations, things like being diagnosed as having some set of processes, set of symptoms within the DSM, that you have some DSM category. And this diagnostic category is an outcome like a sign. And there is this thing we're going to call a latent construct or a latent variable. You can see this is the problem with having too many cooks, because some of us called it latent constructs and others called it latent variables, and then we didn't notice till it was published that LC and LV are different. But it's the same idea. There are these underlying things that we actually hypothesize. These are not directly observable, but these are descriptions of the underlying dysfunction. And there are true hidden physiological states. This is just because we had physicists, and the physicists will tell us there is a state of the world. We have to actually deal with that state of the world. And this is then driven through putative causes, whether it be causes or treatments. Treatments go as a cause because they drive forward. So you can think of this as driving causation, and this then is inference driving backwards. And really what this is this is the correct way to think about endophenotypes and trans-disease processes. What an endophenotype is, it's not just subcategories of a system. It's actually this latent construct going across from many to many. And these trans-disease processes should be theoretically derived from what we know about neural function. And it turns out there's a very straightforward math called Bayesian causal modeling. I'm not going to go through it or ask you to know what it is. But Bayesian causal modeling is a very standard math that all of the computational people kind of live in these days, that allows you to work both forward and backward and actually create loops of this. And that's the answer, because the RDoC is the latent constructs. And the DSM is one of these diagnostic categorizations. And so what we can do is we can say, yes, this is a reliable statement about some sets of patients. And now what we need to do is ask, what's the relation of a diagnosis to the latent constructs? And to give you an example, I'll go through one example. I had a few here, but I'm not going to go through the other ones. But I'll go through one example just to give you an idea of what I mean. So let's take that OCD, those three kind of OCD that I talked about earlier. We have sets of symptoms, whether they be obsessions, compulsives, anxiety, tics. We can measure this with things like instruments and biomarkers, like a Y-box, or an SSRT, or the new DaW two-step habit learning system, which is a simple game that you play that turns out to distinguish between whether you're using the deliberative or the habit system. And subsets of OCD patients do look differently on that task. And then you have diagnoses, which you can think of as, OCD or Tourette's or OCPD or any of these kind of diagnoses, and maybe you even have multiples of these, right? One of the big issues these days is, as I understand it, is multiple diagnoses, and you have, aspects of each one. And the key here is, and then these things can go back to these latent constructs like anxiety threat processing, right? This third group has much more anxiety threat processing problems, whereas this first group has more model-based, goal-directed, or deliberative versus model-free habit learning problems, right? And you have these underlying latent constructs. And of course, individuals probably have different distributions of all of these. These are not yes-no things. These are complex, large-space descriptions of underlying neural systems. And we know a lot about how these kinds of things work. And what we need to do is connect these up, because what we can do effectively, and this was one of the beautiful realizations that came out, is a prognosis is also a symptom. That is, a prognosis is an observation. And in the same way that we're going to take this stuff and go up, we can come back down and say, given this set of latent constructs, if I change my putative, this is from a different example, but if I change a set of treatment, if I change the treatment here, I can ask, how does that change the prognosis? Right? So I kind of work up and then back down to ask, how does that change the prognosis? And when I do that, what I could say is, this treatment will shift prognosis back and forth. Now, the problem, as I said, I'm going to skip these examples. We can talk about them later. I want to come back to practical concerns here, because the truth is, I don't really think very many practicing clinical psychiatrists or psychologists are going to go and learn Bayesian causal modeling. I'm not actually suggesting that at all. What I'm suggesting is that we actually have a translation sequence where we have some fundamental science that learns what's the relation of these latent constructs with signs and diagnostic categorizations, and what's the relation and how does this whole loop work. This is clinical research. This is stuff that we all do all the time, and we know lots of answers to this, right? There's lots of work here at the U, for example, about what's the relation of AXCPT to latent constructs, to different manipulations and changes within neural circuitry. How does AXCPT inform that is basically the inverse of how does that inform AXCPT. This then would need to get translated into some sort of codification process, some process by which this loop is codified into a loop. This is really what the DSM is doing these days, right? It says, here's all the stuff we've been working on. We're going to create these categories. Currently, the DSM, as I understand it, is kind of checks of symptoms. That's not really necessarily fair. That's my understanding. Remember, I'm a PhD, not an MD. But what we could do is we could write an app, right? And everybody could have a tablet or a smartphone that says, when you actually have in practice, you have your tricorder that says, here's my distribution, here's my measurement, here's the tests that I've done, here's the distribution of probabilities over the underlying dysfunctions, underlying constructs. Now, if I do this test, that will be informative or less informative. It will shift that probability distribution. And if I do this treatment, it will shift that probability distribution, right? So what we need to do is start to create a translational codification process that can do this. And of course, yes, this is a loop, right? This is not something whereby it is forward. It is definitely, as everybody in this room knows, it is definitely a full loop coming back. So what I've tried to lay out for you today is this new idea of thinking about psychiatry, thinking about brain function in terms of computation, right? The idea that we have a computational perspective. What the brain is doing is fundamentally, it's about information processing. And so and then that information processing and how you represent the data matters within your brain. This is why you have these different neural circuits doing different things. That's why when I showed you in the decision-making process section, we had deliberative systems and procedural systems. We have Pavlovian systems. We have reflexes. We have perceptual systems. We have these systems because they are better at different times. A key concept was the concept of the failure mode, which says, given that we know how this works, where are the fragile points? Where does it break? And how does it break? And then at the end, I brought you back to this Strungman idea, which is to bring forward a connection and to think of the DSM as an observation, as the statement of, like saying you have a fever of 102, right? Or you have a score of whatever on the AXCPT test, right? This categorization process is very useful, but it needs to be connected back through this Bayesian causal modeling back to the latent constructs. And I'm going to end there. Hopefully there's some time for questions. The stuff I talked about is in this new book, this Computational Psychiatry book, New Perspectives on Mental Illness. I couldn't find a great picture of it, which was supposed to be out last week, but does not seem to be out yet. We're still waiting for the final, but it's out. It's done. It's just waiting to be printed. That Josh and I edited. All right, I will stop there, and hopefully there's some time for questions. Thank you very much. I'm told that you want microphones. Why don't you pass that around?
I very much appreciate this presentation. This was brilliant.
Thank you.
The job in academia is to avoid reductionism. And we do it till the brain hurts.
Yes.
And so thank you for hurting my brain, because but I want to go back, I want to go to a process that researchers have always used, which is observation and latent variable, or observation and endophenotype, or observation and causation.
Right.
We've been doing that forever.
Right.
And the iteration between those processes moves us forward. And so as complicated as this was, it does take into at least in my way of thinking, all of those iterative processes. Now tell me how I move forward.
Right. It's a great question. So I agree completely, and that was why I put in that point about endophenotypes and transdisease processes, right? This is in fact nothing's new under the sun, right? This is, in some sense, the key here and the key difference here, and I do want to kind of say what is different. What's different is those latent constructs are, at some level, computational and neuroscientific. So as I understand, and again, this is probably not fair, as I understand it, most of the constructs that are underlying many of the psychiatric stories these days are from early psychology. And I don't know if that's true, that's been my impression. And what really needs to happen is to connect up with the neuroscience that has moved very far forward in the last couple of decades. And so we now have not just kind of big box and arrow diagrams about executive function, but, and not even the details of that, but in fact the whole process and the neural circuit, and we know which structures are involved, and so you can go in and say, okay, if I do an fMRI, an MRI scan, and I look at the connectivity, the functional connectivity between prefrontal cortex and hippocampus, I should be able to predict how deliberative you are, and if that's not very good, then I can actually provide treatment by providing working memory treatment. And so this patient needs working memory treatment, and that patient needs something else. So for example, as a concrete example, my lab has been looking at a thing called contingency management, which is a treatment whereby you basically pay people not to take drugs. Right? This turns out to be one of the best treatments for this. And the idea is that they come in clean, they come into the clinic clean once a week, and you give them a prize. The weird thing, and the economic story of this has always been, well, you've made drugs more expensive. The problem is it doesn't work. The mathematics of that, again, this is a computational statement, the mathematics of that is just wrong. If we raise the price of the drugs on the street by the same amount, it doesn't change how much drugs they use. But there's something about coming into the clinic once a week and thereby getting paid. And we think it's because it's a shift between decision systems. You've basically changed the decision from, do I take drugs or not? How much, is it worth X amount of money to take drugs? Versus, do I take drugs or go get that gold star? I can go get that gold star. And once you've shifted into that deliberative system, we know what neural circuits are involved. We know how to test if somebody's deliberative system is good. So now you could come in this concrete example, you could come in and actually test, is their deliberative system good? If it's still good, maybe we can actually put them in contingency management. If it's not good, maybe we could train it and then put them in CM. And so the devil's always in the details, right? And the key here is to actually start thinking of this in that perspective and start creating probably the right answers to create teams of clinical, neuroscience, computational, and actually try to find for each specific thing, start to find those pieces to move forward. And a large part, what's happened is we have these silos where people, haven't really been playing together and need to be. I don't know, does that help?
Well, that was as complicated as the presentation.
Unfortunately, the devil's always in the details. There was a question over here.
I guess my question just piggybacks on that a little bit, because as you were talking, I could just hear these proverbial silos like exploding, because I think in this room alone there would be 100 papers, because the clinicians here are thinking about models, maybe not mathematically, but functionally, and what we're missing is that partnership to translate it to database mathematical models. And I was just curious from a practical standpoint, do you and your lab members and teams, you're open to receiving emails, you're open to setting up meetings, your bandwidth can accommodate that? Because I imagine your inboxes might be blowing up after this.
I'm always open to that. Personally, I'm always open to that, but there's also a lot of people here who do that kind of stuff, actually, living in the neuroscience department, living in the psychology department, honestly living in other departments as well. And a large part of what we need to do, it's not just the mathematics of it, but actually thinking of it as a computation, right? And asking, what are the computational changes that are happening underlying? What's the underlying latent construct, latent variable, latent piece, and how is that changing? And yes, quantitative methods are always useful, but honestly, you can do quantitative methods on a Y box, just like you can do a quantitative method on a MRI, just the way you can do a quantitative method on a 100-cell neural ensemble. At some level, it's not the quantitative methods that's the key here. I think it's actually the connection to the neural circuit. And the point being that if we're going to translate to things like genetics, and to things like pharmacology, and to things like, environmental changes, what we need to do is we have to look at how are those changing the brain function, the neural circuits of the brain function, and how are those neural circuits changing the computation, right? Think of that epilepsy example I was given, right? So when people try to take epilepsy to genetics, it's a nightmare, it's a mess, it's complicated, right? But if you can find where is that excitatory inhibitory misbalance, suddenly things kind of come back together, right? Because they all get kind of funneled through that piece. And so what we need to do is find what for each one, and of course that's the hard part, right? Is for each one, what is that piece, right? And so we can give examples in various cases, aspects of addiction, aspects of not even all of addiction, but pieces of addiction. One of the big arguments we've been making is that many of these things are symptoms, not diseases, right? That there's many, or like the OCD example. I gave an OCD example, right? So what is the individual's distribution across those three problems, and how do we treat those three problems? My guess is those three problems would be probably easier to treat separately than they would be to treat as an OCD question. Maybe that's the right way to say it.
Yes, thank you very much for your presentation. It was really stimulating. I haven't had a chance to do the formulas yet, but later. I'm interested in your career as a wordsmith and how that might be related to what we're seeing here. I'm doing some low-tech research using single or non-semantically related words to probe narratives. And just for example, because we have all this politics going on, I've analyzed in that fashion all the three major figures, Obama's words, Hillary's words, and Trump's words. And they turn out very profoundly different profiles.
I bet they do.
And so I'm just wondering, oh, and then there's another notion, I just became acquainted with it, has probably been around for a long time. The brain is a word cloud.
Okay, so let me
Comments and questions.
actually, can I answer that? Because okay, go ahead.
One thing which was not apparent,
Right.
so one aspect which was not apparent, I suspect it's embedded in this notion of the trajectory, the longitudinal trajectory of the individual, is narrative,
Yep.
right? So,
Yes.
individual narrative.
Yes, I don't want to feedback. We'll avoid feedback. Yes, absolutely. And narrative is a fascinating piece. We are narrative creatures. Narrative changes your decision. Actually, one of my favorite examples of this is there's no such thing as one drink for an alcoholic, right? That statement is a change in your narrative. And so somebody who, think of Jekyll and Hyde, right? Jekyll does not want to be, right? Everybody knows Dr. Jekyll and Mr. Hyde. Dr. Jekyll is a geek. He's a nerd, right? He takes his drink. He turns into the evil Mr. Hyde who does horrible things. Jekyll doesn't want to be Hyde. What Jekyll wants to be is Senior Suave. Jekyll wants to be the cool guy at the party. Jekyll wants to go out and have fun and have all the, ladies chasing him and have one drink, but he can't, right? And so the narrative statement of, well, you don't have the choice of Senior Suave, you have Jekyll or Hyde, maybe lets Dr. Jekyll actually become satisfied with being Jekyll and staying home. And narrative is a key factor. Narrative both in terms of our construction of our past and our future. And in terms of narrative, what I will say about narrative is, I'm going to be careful with this. So right now, the neuroscience of narrative is very limited. The neuroscience of trajectory is very, very limited. What we do have is excellent models that seem to be quite accurate and seem to fit data quite well about discrete events. That is, the state of how do I recognize a category? How do I categorize a single moment? Those, they call them schema. They work, and we understand how they work. We understand in terms of categories, in terms of the difference, in terms of their relation to language. I mean, we're still, like a lot of the stuff, this is the beginning, there's more to do, but we're pretty far there. We're far enough to start to talk about. Narrative is something that we just don't have a handle on, either psychologically or computationally or neuroscientifically at this point. And that is very much where the neuroscientists, the basics, the fundamental scientists need to be working. There are some people who've done models of how changes in narrative can change your choice sequences. They're limited. We've done some. They're limited. So, for example, things like pre-commitment. Why does pre-commitment work? Turns out you can make statements about the necessity of having multiple decision systems. If you don't have multiple decision systems, pre-commitment never works. Pre-commitment, by the way, is this idea that I know I'm going to make this bad choice later, so I'm going to make a different choice now to prevent myself. I'm not going to go to the bar, because if I go to the bar, I'll drink, right? Actually, from a classical economics perspective, that's weird, right? You have a shift in your decision systems. And you can prove that you have to have multiple representations of value, you have to have multiple decision systems in order to be showing something like pre-commitment. But that's about the limited level people really have a grasp of narrative right now. In terms of thinking of it as a word cloud, I think there are better computational models that one can do based on basins of attraction and neural network systems. Honestly, a lot of it is what we now call deep learning, or we used to call parallel distributed processing back in the 80s. But it's basically networks of neurons and how their processes and how they work in a high-dimensional space. And this mathematics is very well understood and seems to fit data tremendously well. In fact, it explains a lot of things like the incompleteness of memory, and how memory is reconstructed, right? So the famous, for example, Elizabeth Loftus experiment, where asking somebody how fast two cars crash together changes whether they remember broken glass or not, right? This is a classic 1970s experiment. And we can explain that from these content addressable memory basin of attraction neural network models. But that's not a narrative. That's not trajectory. And that narrative trajectory stuff is wide open. If anybody has ideas about that, I'd love to talk about it personally. But it's something that we don't, as a field, have a good handle on right now. There's a question in the back. One more question in the back. Go ahead, I'll repeat it.
So, when you talk about these ordinance decision-making systems, you said you don't have a great grasp of why one drives behavior in a compared to another. Is there any information on whether there's any common patterns of sequencing that might correspond with, say, course of illness? So, for instance, like something can start at develop through Pavlovian conditioning and become habit learning over time. Do you
Yes.
have any information
Yes.
on that?
So that I can answer very easily. That one I can answer very easily. So the question was, given that we have these multiple decision systems, and I said we didn't really have a good statement of which one, how to decide which one drives when. Are there actual trajectories through learning and stuff? And the answer to that is absolutely. In fact, what we do have is if I run this behavior sequence, this system is more likely to be active. And if I run that behavior sequence, that system is more likely to be active. One of the things that was surprising in the field, comes from about 30 years ago now, is that it doesn't go from habit to deliberation, it actually goes from deliberation to habit. As you learn something, you learn the structure of the world, you learn a map of the world, and you plan within that, and as you get used to that, you build habits within that. The habit takes about 10,000 hours. That number turns out to actually be true. I was really surprised when I went back and found the original data on that. But we know that. What I meant when I was saying we don't know which one is we know that you can do things like contingency management that can help shift you from one system. You shift from Pavlovian or habit into deliberative. What we don't know is that because the part of your brain that drives deliberation overrides the habit? Is that because there's an executive system sitting on top saying, okay, today you're going to do deliberation, no, let's do habit? Or is there actually some sort of parallel system? All of these are what we call distributed representations. That is, they're not a single, communication line like an HDMI or something. They're actually a whole population of neurons. And there's a mathematics, which we developed, which is very straightforward, where you can actually basically ask, do all the neurons agree with each other? And so a third possibility is that all the systems are sending information down, and downstream networks are basically only listening to the ones that agree with each other. This is the kind of thing that we're still working on. But in terms of the trajectory through learning, that actually is well established, and we know what to do. And in fact, if I want to drive you to be more habit-like, we know what we have to do in order to do that. So from a clinical perspective, saying somebody's got too much habit, I want to get you more deliberative, we know very easily how to do that.
So yeah, this is probably a great place to stop. I want to thank all of you who came. First of all, it was very gratifying to me to see such a good turnout for these grand rounds. So that's very exciting. I was very excited to hear your comment, Kaz, because I think it indicates that there's a bubbling interest in creating new shifts in how we think about our clinical work within the department, which is obviously a goal that many of us have. And I think, David, I want to thank you for an outstanding kickoff to this new way of thinking for the department. What I want to say to everyone is stay tuned, because we're going to be using this new narrative for how to approach the actual evaluation and conceptualization of how we should be working with patients here. And I think it's a chance to really do something which is very much at the vanguard of the science for our field. So thank you, and I'll look forward to working with you on this.
Thank you. Thank you very much.
You have been